start the second part of the tutorial. So I hope you could you managed to access the answer sheet from yesterday, in case you needed to fill some blank cells, because we will need what we did yesterday to pursue the tutorial. Okay, so let me share screen. Okay. So, all right. So if we take again yesterday's tutorial, I think what we would need to do, because Colab will disable your virtual machine where the tutorial is after a while, after I think 1 or 2 hours. So I don't think you can now have in memory the results, the models, and the variables that we used yesterday. So I guess you will need to rerun all this. So please open your tutorial and rerun the cells. Okay, so imports and seed value for reproducibility. Okay, then mount drive in order to give access to so give access to your drive, download the data set again from the website. You can run the different cells to create X and Y. So this one is not very necessary for the rest. Print the NaN values, but what is necessary for us is to drop the NaNs and to drop also in the corresponding Y target output variable. Then perform one hot encoding on the categorical feature variables, those 3 variables. Then perform train test split. Okay. So it's not super necessary. So visualization, we won't need that. Summary statistics won't need that. Correlation won't need that. Okay. So this was just a visualization, basically. We didn't modify the data set. Okay. And once it's done, so you can run again the logistic regression model. The support vector machine model. And the k-nearest neighbors model, right? So, oh yeah, we had the code to select a good K. But what is needed for us here is to run this fine-tuned model with the selected number of neighbors, which is 9. Okay. Okay. And so first, before starting multilayer perception, so you will need to go through this. So let me know in the chat box if there is issues with that already, or if you managed to rerun yesterday's cells. Let me know if you have questions. Give you some time to get all set so that we can continue the tutorial. So today the goal is to first implement using scikit-learn the multi-layer perceptron, so classifier. So it's one of the few deep learning models that are implemented in scikit-learn, so we can use it. If you want, in the correction, I can also provide you some code to do the same kind of implementation using another software, Keras, where you can follow better during training the evolution of the loss and accuracy to have access to the same kind of plots that Ronald and I showed you this morning, to monitor the loss, the training loss, and the validation loss through epochs. So, if you're interested. Okay. Any questions so far? No issues? Okay, so if you manage to rerun yesterday's code, now what I would like to do is to try to answer this question, where you will use the same kind of code structure as we saw yesterday, but to implement a multi-layer perceptron, so full connected neural net, to predict the target variable y, which is so the binary output on whether the patient survived after 28 days in ICU from the observation data X that we just simply cleaned and encoded. So yes, so I ask you to create a model pipeline that performs both data normalization and applies a multi-layer perceptron. And I would like you to look a bit at the documentation of this multi-layer perceptron classifier model to adapt the following hyperparameters. So for instance, I would like you to create a model that has 2 hidden layers, one with size 1024 and for hidden layer 1, and one with size 512 for layer 2. Then as optimization algorithm, I would like you to try to use mini-batch stochastic gradient descent that we saw yesterday. And then as optimization algorithm, I would like you to try to use mini-batch stochastic gradient descent that we saw yesterday. And then as optimization algorithm, I would like you to try to use mini-batch stochastic gradient descent that we saw yesterday. with a batch size of 100 items. And I would like also you to look at what parameters to tune in order to have an adaptive learning rate. So as we saw also in the slides like from yesterday and this morning, to have a larger learning rate at the beginning of a training and then reduce it once we get a bit closer to good parameters estimate. And to adapt the number of epochs, which is the number of training iterations of updates of the model parameters of 2000. Then once you've done that, you can fit the pipeline on your training data, exchange, and evaluating on validation data. Yeah, similarly to yesterday. So I encourage you to look online, to open a tab in your browser to look at the scikit-learn documentation in order to know how to adjust for the different following hyperparameters. Can let you think for 5 minutes about this. And do not hesitate to raise questions. Also, if you had issues with rerunning the tutorial, do not hesitate to raise questions. If you manage to find a ROC AUC score, do not hesitate to share it in the chat box with the rest of the participants. Okay. No questions, no problems, no answers in AUC score. Do you need more time or do you want me to share the... okay. Still trying. Okay, okay. Okay, Yingli, did you manage to rerun the previous cells? Are you focusing on this question? Trying for a new question. Okay. Okay, so I'll let you some time. No problem. Can really like yeah, manage to rerun previous one. Good. Good. So yes, for the parameters, you can look. You will get the answers from the documentation, and for the code itself, it's very similar from what we did yesterday. Okay. If anyone managed to have a AUC score, please feel free to share. Still running? Okay. Oh, because maybe the number of epoch is a bit... It's taking a while, Zhengshu? Okay. AUC score, okay. Why do you say, Zheng Shi, that your code has something strange? Because of the performance? Yeah. I mean, it's not meant to. The parameters I gave you are not necessarily meant to optimize the score. I wanted you to also make a link with what we discussed during the lectures, like the optimization algorithm that we saw in the lectures, etc. Yeah. And actually, I realized that the cells I run on my side was not with the exact same parameters than the ones I provided you. I'm doing it. How long did it take for you to train? Around approximately 2 minutes. Okay, 2 minutes 20. Okay. Do you want me to share the answer now, or do you want a little bit more time? Or is it because it's still running for you? Take some minutes. So you can see here, first thing we can see is that it's taking it can take quite a while if we put a lot of epochs. So here I put you 2000 epochs, so it's quite a lot. But you can realize that it's can easily take quite a while to run, especially imagine if you have 1 million example. So here we are using only CPUs as computing resources. So yeah. Okay, Yingli, you can try. No problem. But your code, okay. Oh, so you find okay, 74 AUC. Let's see. Did mine complete? Okay, I think mine completed. I'm going to share again. Okay. So I obtained on my side 73 for AUC. Do you know what's different between your code and mine? Oh, normally, okay. That's the only difference for you? Interesting, because normally the first, the second cell of a tutorial would allow to put a seed for scikit-learn. So interesting. Maybe if you can try with this random state just to see, let it run and just to see if it makes a difference. But basically here you see that all the many concepts that we were introduced in the slides can really be integrated here when you do a multi-layer perceptron model. Like you can pick different solver, like stochastic gradient descent that we introduced. You can put a constant or an adaptive learning rate. You can modify the batch size, modify the number of epochs, etc. So, and modify also the shape of the multi-layer perceptron to make it deeper, to increase the number of hidden layers, and adapt the number of neurons in each layer. Okay. Yeah, here I tried with some other parameters. Never mind. Yeah, so I'm not sure you get this session in your version of the workshop slide, tutorial. Could you please let me know? I think I removed it from. Okay, so yeah, this was to go further. So something that I could share with you after, or if we have enough time here, it's to implement the same kind of multi-layer perceptron model, but using Keras library. So basically the idea, so I commented here, but the idea here is then that you can build models in a more modular way using Keras. Because it was really made for deep learning. So yeah, many very experienced people prefer PyTorch. Keras to me is more accessible when you start. So yeah, the idea is then you can really create your own model by adding input layer, then several dense layer. You can add a convolutional layer when you need it, and you can adjust every step of the way and adjust the activation function. If, for instance, here, because we are classification, the last activation function will be a sigmoid, etc., etc. And you can define also your optimizer, etc. So it's a bit more code to write, but when you want to do a bit more fancier models, that's really useful. And so here I didn't run it, but I could share it with you later, is that with Keras, what you can access, and that I didn't manage to access with scikit-learn, is the learning curve, the history, like the learning curve for each epoch, to look at really when does it start overfitting, etc. This you can see it after you train your model. You can see it with Keras, for instance. And there are also some tools out there that enables you to use, for instance, tensor boards, so that you can look at the learning curve while your model is still training. Maybe your model will be very long to train, like 1 hour, 2 hours or more, or even like the whole night, because you have a huge data set and a huge model. But you may want to be able to look at the evolution. So then there are some tools that are compatible with Keras, for instance, where you can visualize those plots that will be updated regularly along the way. So this, I go a bit more faster. Then, do you have this random forest cell in your? Okay. Is there a question or is there the code already? Sorry, I don't remember. Question. Okay. There's a question. So here I wanted you to implement. We didn't had time during the morning sessions to introduce this model, which is random forest. And it's also not so easy to explain it theoretically. So, but in practice, it's so popular and so very super usually used, especially in a lot of machine learning for healthcare papers, because it works quite well. So random forest is another type of classification model, another type of model that uses decision trees. So I won't go too much, I won't spend time on trying to explain you how it works here. It's not the scope of a workshop. But if you're interested, I encourage you to look out online in books more about how this model works. But in practice, yeah, it's most of the time the model that will work maybe the best on the healthcare data set you have. So, and it's the way you implement it is super similar, is exactly the same. You can implement it with scikit-learn. So I would just, yeah, like you to try to create a random forest model. The question is raised, right? Is written on your tutorial. So yeah, so please try to implement the random forest model using the same type of code as before. And let me know about which AUC, rock AUC you find. Any other questions so far about problems to rerun previous cells or? Or if you have no hard time to catch up with the implementation we proposed? If you have any question, do not hesitate to use the chat box. Okay, so did you use I asked you to use default hyperparameters, right? Let's see. A random state 0. Yeah, I don't know. Yesterday it looked like it worked without this random state thing, just with the first cell. Kind of weird. Okay, So just a normal random forest. Okay. So I guess I agree with you on this point. With a random state of 0, actually. Or very close, right? And yes, so this is the code. So you see it's exactly the same code. So that's the good news about scikit-learn. When you master one model, then it's quite easy to run a whole bunch of models. And yeah, what I tried also is using some different parameters. Scikit-learn also, for all those models, provide you, for most models, these parameters for class weight. So basically, this will introduce some way to give more weight to the lowest class. So in our case, remember that we had only 15% of true labels. So yeah, that's kind of the problem. Also, random forest, one of the first parameters you would like to adjust is the number of estimators. Okay, usually the higher it is, the better it is, but you have some risk of overfitting. Yeah. Okay. Questions so far? Questions about the beginning of the workshop, MLP, random forest? Yes, so you mean weighted case, you mean by default? You mean by default, I guess each model will better perform when the cases are balanced. But when they are not, it may help sometimes, not always actually. It may help sometimes to add some class weight in order to correct for this imbalance. Does it make sense? Does it answer your question? Mm. Yeah, and one thing which is maybe worth mentioning for random forest is that it does not require standardization, feature standardization. It's one characteristic of those decision trees. It performs very well even though the features are not normalized. Okay, good. I was trying if the different participants have different weights. I'm not sure. Maybe I should look at the documentation in scikit-learn. And maybe scikit-learn does not handle this, but maybe it's possible. I think it's possible to put a weight either for each class as we impose here when we say balanced. So just put a different weight for when it's class 0, class 1, put a higher weight for class 1 because we have very few. But I think there is an option to put a weight for each sample individually. Let's see. Wait, for multi-output problems. Sample weight. Where's sample weight? So maybe you can add that in the training, actually, when you fit. Sample weight. So I think this would answer your question, Yingli. Yeah. So really, it's really, I mean, it may seem like natural, but it's really super, super helpful to have such a good softwares in Python to do to implement machine learning, deep learning models. Because you see, every time maybe you want to do something even a bit fancy, you can adjust that. So very useful. Okay, just let me see. I was there, right? Okay. No more questions? Questions on this part or previous parts? Technical issues? Okay. So maybe then what I would, I don't know if I kept this list of models in your tutorial. What I would like to do for the next parts that will help you is to copy this actually. Model dicts, to create a dictionary of the name with a different name of models that we did, and the name of the object that you created. So I don't know if you kept the same names as me. Otherwise, you can modify this by the name you took. So that's why what we trained yesterday, logistic regression, SVM, KNN, that's good that you managed to retrain those so that we can use that for evaluation. Okay, so please copy this. I don't know if I can share it with the. Is it present in your notebook already? Ah, okay, cool. So please run this or adapt the names if you picked different names, adapt it. Oh, I hope you didn't pick the same names for all your models. So run that. We'll use that in the future. And now what I would like you to do is to now we train our models. Okay, so actually 5 different type of models: logistic regression, SVM, KNN, multi-layer perceptron, MLP, and random forest. Okay. So now what I would like you to do in this new part 5, is to do cross-validation, K-fold cross-validation. So a notion that Ronald introduced to you. Because now, until now, what we have done is only to use our training set. We divided it into train and validation, okay? And we just, the only score we have is the score on the validation set. So in order to have a bit more robust estimation of how your model performs, it's better to do K-fold cross-validation, especially when you have very large data set. That means that you split, I remind you, you split your training set, train plus validation, you concatenate it, and you split it into, let's say, K equal 5, like I suggest, in five different sets. And then you will, if you do k equal 5 full cross-validation, you will train 5 models. For each model, you will train on four folds and evaluate on one fold, on the fold that you didn't use. Then that means that you will have, instead of one AUC score, you will have, are these fitted models? Yes, those are fitted models. Because now the idea is to have them trained, and we'll now focus on the evaluation part. Okay. So once you have your trained model, you can, I mean, instead of, let me see. The list of models, yes, I would like it to be the trained models. But for K4 cross-validation, the idea is not to take the trained models, because we trained it on we trained it on a predefined split of train and validation. Here, what we want to do is to redefine the architecture of a cross-validation, redefine the architecture of the model, do the split, 5-fold split, and then run 5 models, okay? So, so actually, you can do it either manually using scikit-learn using the k-fold function to create your split, and then manually do the loop to fit the model, to train the models, and to evaluate them on 5 times, okay? Or you can directly use cross-val score function that does everything for you. So very convenient. But if you want to try to do it manually so that you can really understand, have a better feeling of how it works. Okay. So maybe I'm going to share with you what I did. Okay. Maybe you can comment. So first thing we need to do when we do, let's say, manual cross-validation is concatenate the train and validation sets, okay? So here is just some line to concatenate the matrix X of observation and also the target output variable, okay? Then let's define a pipeline with logistic regression, for instance. So you can either do it directly using scikit-learn using cross-val score, so very convenient. So you just put your whole training validation set. You just precise the number of folds you want and the scoring metric, okay? So that's the way to do it, like in one line, using the scikit-learn function. Another way is to do it more like manually. So first step is same, so you concatenate train and validation, because we will train and evaluate the model on this whole train plus validation set. Create your pipeline, so same. Now we use scikit-learn function to create splits, okay? So you create the splits, and then you need to do a for loop manually. to train and evaluate your your model for each fold. Okay, and then you can print the accuracy for each fold. You can store it and then compute the mean, standard deviation, etc. But actually I have some hesitation here on my code, because to me, you would need to redefine the pipeline every time. Yeah. So what I obtained in the end, so using the one-line scikit-learn function, so I get accuracy score, I can get so the mean, I get the scores for, I get a list of scores, of 5 scores. So here I put you the mean and standard deviation, okay? And then for ROC AUC, for the manual way, I printed the ROC AUC each time and the accuracy each time. Just have some, just have some hesitation. I think to me here, you would need to redefine it each time. Yeah. Anyway, that's the idea. Okay, and I think I remember why I did 2 ways. I did, let's say, automatic way and more like manual way. Manual way, you won't have to do it in practice. It's more like to better understand. It's just because when it's one line, sometimes we don't like really necessarily feel what all the code and all the steps that are behind that. I think what was a bit limitating in this function is that it would only, I think, give you the scores in terms of accuracy. I'm not sure, because I think you can choose this score. Let's check that. It's scoring, as you can see. Yeah, I think when you do scoring here, so you can put different scores, you can put accuracy, ROC AUC, etc. However, I think by default, you cannot choose the metric. I know why. There was something that I thought was a bit limiting here. Maybe not. Don't remember why I did 2 ways. Just to try to have a more sense of what was going on. So basically here in practice, instead of doing just a single training and validation split as we did yesterday. In practice, I would advise you to do K4 cross-validation and to look at how your models perform in terms of the mean and standard deviation after your K4 cross-validation. And I guess it's a more robust way to evaluate your model. Okay. Questions on this? Questions on this or on previous parts? Okay, so maybe what I suggest you is to take a small break, maybe a 5-minute break if you have no questions. Because after this, so we have part 6 with advanced metrics. Let's see. And then we have, so part 7, hyperparameter tuning. Okay. Before just having our conclusion. So let's have a short break and come back at 2:40, 2:45. You can raise questions during the break. All right, everyone's back. So any questions, problems, etc.? No? Okay. So now let's go through part 6, which is advanced metrics. So I don't think there is any questions for you out there, right? The idea of this section was to show you especially the rock curve that Ronald introduced you this morning. So I think I just provided you the code, right? No questions for you on this part. So the idea here, I provided you some code to actually create cross-validation and plot the corresponding rock curve, receiving operator curve, receiving receiver operating characteristic, sorry, curve. So this is what we get. Oops, sorry. Sorry, it does a little bit of warnings. So it's taking a little while because for each I ask it for each models that we trained to do cross-validation and plot the mean rock curve. You managed to run this this code? It's present in your notebook, right? So yeah, the idea here is that for each classifier that we trained, so we want the true positive rates, the AUCs, and for each model, we'll do a cross-validation. So we'll fit the model. And so here I didn't, I won't plot the rock curve because otherwise I will have rock curve for each fold, five rock curves per model, which I think it's not what I obtained in the end. But I need to compute those ROC curves to get some to save some of the values. And then in the end, so I take mean IUC, standard deviation, and I compute, I use this mean false positive and true positive rate, right? And this is what I want to plot for each model. Wow, it's taking a while. Okay, don't remember that. I should have asked you to start running this cell before taking the break. So that's the idea, and then that will plot you the ROC curve. Okay, so let's wait for that. And then another, so nice metric that personally I like to use when I do some classification is to use the confusion matrix. So actually I already did that in the previous cells. So here I just provide you the for loop to plot the confusion matrix for each model that we tried, and I think it's a nice way to quickly compare the models to look at oh, maybe this one is more sensitive, this one is very bad, etc., etc. Okay. Oh. So you have a problem to access X train val train. Okay. What error does it tell you? May I have your X train val shape? Oh, really? Oops. Okay, looks right. Do you have same code as me here? Is the data frame? Okay, yeah, it should be. It should be, and actually the train and val here should be the index of the splits. Yeah. It's a bit annoying. So it gives you quite quickly an error, or does it run like this? Quick error. Okay. Weird. I think train and val, I'm not sure, but I cannot access it. Can access it, but I need to delete this. Okay, I stopped that. Ah. Sorry. Okay. So here you can try to appreciate the rock curve. Taking a while. So let's look at this problem. Because it defines the loop. Okay. Oh, really? What? Sorry for that. I need to get this again. Okay, it should work. Sometimes. Really? Sorry, it looks like my notebook actually died. Sorry for that. Trying to get the same settings so that we can compare. Can look at the type of X train. Country. Okay. Okay. Oh no, MLP. Sorry, change that. Okay. Okay, sorry for that. I need to wait for it to complete. Sorry for this bug. Oops. Ah. Okay. Type train and looks like it's a list. It's an array, yeah. It's an array, so normally train and val will be the indices for the samples that will be in the split. And so what you get here, you're saying me, you getting are in the columns. It's supposed to be in the rows. That's weird. Sorry, like this, it's a bit hard for me to debug. It looks like the error, looks like the code tries to select. Oh, maybe it's no. Ah, okay. Let's try that. Oh, weird. Okay. Sorry for this, and I don't want to take too much time. I'll try to debug that and give you the answer in the answer sheet. Yeah. Yeah, I guess there is some issues where in the train numbers there are not, maybe some are not present in X train, and then it creates an error. And in the error you get with the columns, it looks like it's looking at the numbers in the columns instead of the rows. That's okay. Hope you got the chance to look at the rock curve. So it's a way to plot the rock curve. And then, did you manage to get the confusion matrix? Just a way to summarize what we get. Okay. And maybe so last part, which actually, so if we don't, you don't, no questions anymore about the metrics. I'll try to debug this code after the tutorial. All clear? So it's basically how just to plot some curves with different metrics that we saw. And then the last part that we didn't really introduce in the morning slides is a practical problem, which is hyperparameter tuning. Because I guess maybe yesterday already and today, you saw in this tutorial that we can implement machine learning models or small neural networks, but then there are many different parameters, hyperparameters that could be set. The shape, the learning rate, the type of optimizer, I don't know, like for the SVM, the kernel you use, the regularization you use, etc., etc. And it's very hard to know which parameter to take because it will depend on your problem. And it's very important to find good hyperparameters because, as you saw, in most of the models we tried, we only put default parameters and the performance is super bad, close to random, right? So what is done in practice to find good hyperparameters is to do a grid search. So that is to define a grid of parameters that you could try. So for instance, logistic regression, regularization L1 or L2, and maybe the coefficient of regularization 0, 1, 1, and 1, and 10, for instance. You don't know how to regularize. So you can do trials. So what you can do, and with scikit-learn you can do that, is to create a grid of parameters that you want to consider, and then train in cross-validation, train and evaluate your models with these different parameters, hyperparameters. So you train a lot of different models with different hyperparameters, you evaluate them, and then you take you pick the parameters that seem to be the more adapted to your training data. Okay. This would increase the chances for you to better generalize on the test set, right? So in practice, it is super time-consuming step, and not the sexiest part, but that's how it is. And what you can do also for research, because sometimes you have so many hyperparameters, it's too long to try every combination. So there are some options in scikit-learn to do random grid search. So not to try out every possibility, but a good amount. or you can have also some more complex research, more complex random picking of parameters. Okay. So I don't know whether here in your version you are asked to do the hyperparameter yourself, or whether the code is provided. I only have a question. Okay. Yes, what I would like you to try here is to create some grid search on logistic regression pipeline, okay, to find the best regularization L1 or L2 that we introduced yesterday, okay? L1, L2, and strength of regularization. And to evaluate each models, you use K5-fold cross-validation, and you optimize using the ROC-AUC score. So to do this, I would suggest you to use scikit-learn function, which is something like research. Let me check. Okay. So you can use this function, research CV. Okay. You can look also at examples. I guess there are some examples. You see, they say they. Yeah. I guess here you have some examples you can get inspired. Okay. So this function will help you for a given estimator, so a given model, for a given grid of parameters that you will define, to select, to find out which are the best hyperparameters. So here we focus on selecting the best regularization. So I give you some time to think about it. If you have questions, do not hesitate. Okay. Do you manage to create some hyperparameter tuning code? You have some problems? Questions? Do you want some more time, or do you want me to share the code? Um, oops. Okay. How does it go? Do you manage to find something, or is it a bit too tricky? Or is it all running? Do you want me to share the code now, or more time, as you wish? Failed to generate the code. Oh, maybe now. Okay, okay, okay. So let's look at how we can do this. So basically, to do a hyperparameter tuning, so first you need to import the grid search CV function, right? Then yeah, it's not like super easy actually to do it. This is so some code that I propose you. First, you need to create a dictionary of parameters. Okay. Actually, you need to give a name of the model, underscore, and the name of the parameter. Okay. So for instance, here I put actually a bit more stuff. I put, so the strength, this is the strength of the regularization. Right. This is, so the type of regularization. Okay. Then I added a few more parameters like the class weight or the solver. Okay. Then you need to declare a pipeline also. So to be honest, I don't know why I removed the scalar anyway. And to do the grid search, you need to do this. Resource CV, pipeline, so which is your model, basically. Cross-validation fivefold. N jobs -1, this means that please use all the computing resources available. So if you have a lot of parameters that can help you finishing the grid search earlier. And param grids, so you give the following parameters, okay? Scoring here, I put F1 score, but actually you can put like whatever you prefer. Okay, could put rock AUC. Okay, and then maybe here I can copy for you to put exactly what I asked. Okay, this was just L1, L2, right? You can put none. Okay. And it was rock AUC here, right? Okay, so it's not very long. Basically, this code will provide you, so then the grid, when it's trained, you can print best parameters. So it's the parameters that gave the best rock AUC score in terms of cross-validation, of k-fold cross-validation. And it prints here. So it gives you the answer, which hyperparameters, combination of hyperparameters is better to consider, okay? May I ask you, what does it mean by F1 macro comparing to F1? Yes, so F1 macro and F1, I always forget what it means. Basically, F1 macro will be the F1 that Ronald introduced you. And F1 micro, I think it makes sense to distinguish between micro and micro when you have multiple classes. Because then it will compute it, I think, per class, something like that. Not quite sure. We can look. It's the definition of F1 score. And then, yes. So then you have micro and micro. Actually, here we could put binary, right? So I think it's relevant to distinguish when you have multiple classes. So it says it does not take in label imbalance into account. When you have multiple, like 3, 4 classes, it does not take. imbalance into account, while micro computes the matrix globally. Okay, but I think maybe here actually binary would be more suited. Okay, you're welcome. Where why I was here, right? No. Oh, answers. Okay. Okay. So is it clearer for you how to build hyperparameter tuning to implement hyperparameter tuning? Okay. Okay, so here actually the good news was it was quite fast to do because we had only a few parameters. They can be actually very, very long. So maybe here in the answers, I did some more parameter tuning. Maybe what I would propose you, because it's super, super long, it takes like more than 1 hour. So maybe what I can propose you is to share with you the parameters I took that I found in the end after parameter tuning. So using this same type of code, just adding parameters and replacing, I did it for SVM, super vector machines as well. So, yeah, I think here, so I created here, logistic model fine-tuned. So maybe I'll share in the chat, so it's not like super great to do that. But maybe what I can do is this. This is the parameters I took for logistic regression. After parameter tuning. Oops. And for super vector machine, so basically the code will be very similar to what we did previously. It's just, then you can put, for instance, different kind of kernels, class weight, then so some parameters. Then you really need to look deeply into the documentation to look at all the parameters. Sometimes there are also books, blogs, etc., tutorials that give you an insight of which parameters are very more important to tune. Okay. And here is what I took for super vector machine after fine tuning. Right. Okay. If you don't want to like redo everything because it won't finish before the end of the session, basically. So what I would propose you to do is to create model pipe SVM fine-tuned with the parameters I shared, and model pipe logistic regression fine-tuned with the with the parameters I shared. Okay. So it's a bit messy. Yeah. And this is a fine-tuned one. And for MLP, multi-layer perceptron, I choose this. Okay. So you can also here get a fine-tuned fine-tuned model. It does not guarantee you that it's the best hyperparameter, though. It depends on the grid you picked, etc. So it can take time, yes, and maybe sometimes you see that you try, for instance, regularization 1, 2, 3, 10, and you realize that 1 is already too high, so you need to refine your grid, etc. So it's very, very time consuming. Okay, and so I just shared the results with you here, the hyperparameters, just so that you can try to do the final model comparison. Okay. Yeah. So the idea here is like once this is trained, sorry. Okay. 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 Maybe this one, the MLP will take a bit more time to train. Oh, not so bad. Okay. And then in the end, you can combine, recreate a model dictionary with that adds all your fine-tuned models, MLP fine-tuned, SVM fine-tuned, and logistic regression fine-tuned. For visualization purposes, you can, if you wish, plot the confusion matrix to have a quick look on the confusion matrix for each model. And then the idea, so I think I provided you this in your tutorial as well, is so to summarize all the results in the pandas data frame, so then you can look at all the scores, etc. So basically what I did is I create a data frame, pandas data frame, from the dictionary, and this is the dictionary. So first we have a model. So it's the list of models names, okay, model keys. Then I wanted in my result table to have a 5-fold cross-validation accuracy. So then the mean accuracy. So this is how cross-val score. I take the mean cross-val score of the model, okay, for the X trained validation data set, 5-fold cross-validation using accuracy for each model in the dictionary, okay? And then here's the first time that I will use the test set, right? So it's really in the last step. Normally, once you have picked a model, fine-tune the model, that you are allowed to look at the test set. Otherwise, you will overfit. So you usually really spend a lot of time on fine-tuning your model before applying to a test set. So in your test set, you have plotted the test set accuracy, so score for each model, okay? Then the ROC AUC score in test for each model, and F1 score, okay? And when I do that, this is the table I get, okay? So I hope you can manage to get this table. At least if you didn't manage to do the fine-tuned version with at least the logistic regression, SVM, KNN of yesterday. And then here you have your list of results. So it's nice, it creates you directly the summary table, okay? And here's the first time we look at the results on the test set, right? So can you do any questions, problems? Any comments on the results? Stuff that feels surprising to you? Sounds surprising? No comments in mind? No questions? So actually, if I do some comments, first, let's note that the accuracy may seem very, very high, but we need to keep into account that our test set, our data set is imbalanced, right? So the default accuracy is not 0.5. On the other side, the ROC AUC, default ROC AUC is 0.5, okay? So we see here that basically logistic regression seem to perform quite well in tests. SVM also quite surprisingly, actually. But however, when you see like finally SVM fine-tuned seem to overfit because we have a quite good result in cross-validation, but not as good in tests. When the MLP is fine-tuned, also this performance is pretty good. Random forest performance is pretty good as well. KNN on this dataset does not seem to be to perform well, or at least not with the parameters we tried. Maybe with another, we need more. We need other metrics, distance metrics, etc. Maybe the default metric is not adapted. So that's an idea. Any questions, comments? All right. So here with this cell, I just wanted you to show, to try to show in terms more in a more visual way than numbers, but actually it's not super compelling. But yeah, once you have your result, you have several ways to present them, bar plots or other kinds of charts to summarize your models, right? Okay. Any question? Any comments? Okay. So if not, I'll just try to make a small conclusion, small comments on this tutorial. So first, what we see in results as a result of a model performance is that the performance of our models is very low, is very poor. Keep in mind that we are in a highly unbalanced data set, so that the default accuracy is around, should be around 80%, 85%. So our models are actually performed close to random. But then what explains these low performances, what could explain that, is that we didn't focus on feature engineering. Okay, we just quickly cleaned the data set and coded the data set, but so drove the missing values, etc. But we didn't do, we did only visualization, but we didn't really do any operation on the features. Okay, it would have been too long for this workshop. However, it's also a good, I guess, educative way to realize that this is a really important and crucial step that in practice you need to spend a lot of time on. Okay. And finally, maybe you can try to answer, can those results give you any hint about how these models will perform on another healthcare dataset? For instance, here, if we found that the MLP of a random forest performed best, can you think that for another data set, those ones will perform best as well? Any idea? Yes, no? No idea? Yeah, thanks, Zheng. No, yeah, actually, you're right. So the model is really dependent on your data set. So an architecture that does not fit well your data here or clinical data that does not mean that for another data set, this model will perform better, will perform bad as well. So you really need to explore, to look at your data, to maybe look at, depending on like the number of outliers, the nature of features, etc. Try out different models that are well suited to your data. And then, yeah, look at which one performs better on your training evaluation data. But you have no guarantee that if a MLP performs well on one training data set, one problem, it will perform well on another problem. That's the idea. Okay. And so that's the end of this tutorial. So if you have any more, if you have some final questions, let me know. Otherwise, I don't know, Ronald, do you want to do some break before switching to your part?
Yeah, how about 5 minutes break? So we'll be back at 3:45. Okay.
Okay.
So see you at 3:45. Okay.
Okay. Thanks for your participation.
Okay, so hope everyone is back. So good afternoon, everyone. So in the chat box, I have shared a link where you can download the code for the model evaluation part. And there is also another link, the second link, where you can find the dataset split that we do. So please download it as well. But otherwise, you may need to rerun everything from scratch. Okay. And there are also another 4 links where you can download the 4 models that have been trained on our train set and further fine-tune on our validation set. So if some of you did not manage to build the models by yourself, please download the 4 models, okay? But if some of you have successfully built your own models, then feel free to do the model evaluation part on your own trained models, okay? So probably I will give you 5 minutes time to download everything and put it in your own Google Drive and open it, okay? Oh, please let me know if you cannot download it, okay? If you have some trouble download it. So have everyone download everything and put it in your own Google Drive and open it. Okay, so I will assume that everyone has downloaded it and put it in their own Google Drive and then open it, okay? So let's start. So yesterday and just we all have developed 4 different machine learning models, logistic regression, support factor machine, k-nearest neighbors, and neural network. And we train it on the training set, and we perform hyperparameter tuning and evaluated them on the validation set and as well as test set. But as we have learned some evaluation metrics in the morning session, right? So now let's use some of the evaluation metrics that we have learned in the morning session to measure the performance of all the 4 models, okay? But first of all, let's do some environment setup. So first, we need to import all the relevant libraries, right? So let's run it. And second, we need to fix the random seed value, right? But actually in this case, we don't need it, but we just run it, okay? And lastly, we need to set the working directory, and note that you may need to change this directory based on where you put the files, okay? So for me, I put it in this folder. So I add this one, okay? So let's run it. Okay, so actually, as Hanae has shown you some, so there are some libraries that we can use to compute all the evaluation metrics that we have learned. But for this occasion, for a better understanding, let's define our own function to compute accuracy, sensitivity, specificity, PPV, NPV, and F1 score. But for the ROC curve, because it will be a bit difficult to implement from scratch, so we can just use the sklearn library instead, okay? So as all the functions that we are going to build have the same inputs. So there are 3 inputs. So the first one will be the y, which is the ground truth, which is either a value of 1 or 0. And the pred, which is the output of the model, or so which is the output of the model, which can be any value between 0 and 1, indicating the probability of a patient to be predicted as 1, okay? And the last input variables will be threshold. So this is the cutoff value for positive prediction for the model, okay? So for examples, we set our threshold at 0.5 and we got our pred as 0.7. Then for this patient case, we will predict the patient to be predicted as 1, okay? So for the rest, starting from accuracy to F1 score, we all have learned that these metrics are actually can be computed based on the value of true positive, true negative, false positive, and false negative, right? So now let's wait. So now let's do some exercise. So by defining 4 functions to compute these 4 values, okay? But first, I have given you an example about how to compute the true positive here in the code. So basically, first of all, what we need to do is to get the thresholded predictions, okay? So as I mentioned before, if our threshold is 0.5 and our predictions is 0.7, the pred is larger than threshold, then we'll predict as 1. But if the prediction is below the threshold, then we will predict as 0, okay? And after that, to compute the true positive is pretty straightforward. It can be calculated as the sum of the patients whose y is equal to 1, and at the same time, we predict it as 1. Okay, so it's pretty straightforward. And for the other three values, what you need to do is just to change the known statement here with your own computation about how to compute the true negative, false positive, and false negative. Okay, and for this, perhaps I can give you 5 minutes time to do your own computation, and after that we can check our answer if we have the same answer or not. Okay, so I give you about 5 minutes time, and good luck. Okay, and if you have any question or you encounter any problem, feel free to ask in the chat box. Okay. Okay, so time is up. Hopefully you can get everything right. So let's check if we got the same computation or not. So for true negative, right, it can be calculated as the sum of the patients whose y is equal to 0, and at the same time we predict it correctly as 0. Okay. And for the false positive, then it just calculated by the sum of the patient whose y is equal to 0, but we predicted incorrectly as 1. Okay. And lastly, for the false negative, it is just calculated by the sum of the patient whose y is equal to 1, but we predicted incorrectly as 0. Okay. So let's run this cell. And below, I gave an example as a sanity check to check whether our function is working properly or not. So let's run it. So this is the example, and this is our function's output, and this is the expected results. And as we can see, our number match each other. So it means that our function is working properly. Okay. So we got it right. And hopefully you too. Okay. And for the rest, from accuracy to F1 score, it is another exercise for you. And as I said before, like all these metrics can be computed based on the 4 values: TP, FP, FN, and TN. Okay. And so first, I will just give you an example about how to compute the accuracy. So it is pretty straightforward. The first thing we need to do, because accuracy can be computed by this equation, right? So we need all the 4 values: TP, FP, FN, and TN. So the first thing we need to do is to get the values for these four variables, right? So we can just use our own function to compute it. So it would be like this, and then we put the input variables inside, which is the y and the prep and the th. Okay, and it would be really similar for other 3 values. So you can just copy and change the function name. So it will be false positive. This will be true negative. And this one would be false negative. Okay, and then finally, we can compute the accuracy using this equation, right? So we can just copy this and then put it right here. And we can run the cell. And we can check it with an example below. So, right, so for this example, if you want to compute by your own self, you can get the accuracy of 0.6, and our function's output is also 0.6. So we compute it right. So for the rest, from sensitivity to F1 score, it's your turn to exercise. And then I will give you like 10 minutes time to compute everything. And hopefully by then you can get it right. Okay. So let's do it. Okay, so time is up. Hopefully you can get all the answers right. And I have provided a completed code in the chat box. So you may or may not look at it to check whether your answer is right or not. And you may or may not want to open it as you wish. As long as you get everything right, then it's fine, okay? So I just want to talk a little bit about the ROC curve, because as I mentioned before, it will be a bit difficult to implement from scratch. So we can just use the sklearn library instead in specific these two functions, okay? So for example, you want to compute the AUC ROC of a model, then we can use this function named ROC AUC score, and the input variable will be our ground truth Y and our prediction, our pred, or the model output of probability. Okay, so we can run this cell to give us an example. So yeah, we got the AUC ROC, and if somehow we want to plot the ROC curve, then we can use this function named ROC curve, and the model input will still be the same as before. And this function, right, it will output three values. The first one is false positive rate, and the second one is true positive rate for all possible threshold. Okay, and the third one is the threshold itself. But if we just want to plot the ROC curve, then the third values will not be important for us. So after getting this set of false positive rate and true positive rate, we can just use the matplotlib to plot the ROC curve. Okay, so we can just run this cell. Okay, so we got the plot of the ROC curve of our model. Okay, and this blue dotted line, right, it's called something called no skill line, where we predict either 0 or 1 for all the test cases. Okay, and it is a good benchmark to compare with our model, because if our model even cannot beat this like no skill line, then it means that our model is not good enough. And in our example, our model, yeah, did not perform well enough, because in terms of AUC ROC, it may not have like higher AUC ROC compared to the no skill line, right? Because here we only get 0.42, which is lower, even lower than 0.5. Okay. So now we have defined all the evaluation metrics, and hopefully by defining our own functions, we can have a better understanding about how to compute and what's the meaning of all these metrics. Okay. And now let's start measuring the performance of the four models. Okay. So the first thing we need to do is to load the test set, or if you're just continuing from your previous work, then you don't need to. But if you want to use my dataset split folder, then you can load it. Okay, and you may want to change the directory as well based on where you put the folder. Okay, so let's run it. So this cell basically just loading the test set and train set. Okay, and next, the thing that we need to do is to obtain the predictions from all the machine learning models on our test set. Okay, so if you want to use the model that Hanae have fine-tuned a couple of times before, then you can load it back, because we save it in pickle file in a pickle format, so we can use the pickle library to load the model back. So for this one, you may want to change the directory as well if you have put it somewhere else apart from the main root. Okay, so this line of code will load back the model, and then after that we can use this predict proba to get the output of our model on the test set. Okay, so this predict proba command, right, it will output two values. So it will output two values, and these two values will sum up to 1. So the first value indicates the probability of the patients to be predicted as 0, and the second value indicate the probability of the patient to be predicted as 1. So as we only concerned about the second value, so we can just retain the second one and forget the first one. Okay, so this line of code is basically doing that. Okay, so let's run the cell, and let's run other cells as well to get the prediction from the SVM, KNN, and also the MLP. Okay. Oh yeah, and if you just use your own model, then you don't need this line of code. And basically, you are just using your own model and get the prediction using this command. Okay. So let's run it one by one. Okay, so basically now we got all the predictions from all the 4 models. And next, we just use our own defined functions to compute all the metrics from accuracy to F1 score. And start from accuracy, and then sensitivity and specificity, and PVV and NPV, and lastly, precision, recall, and F1 score. Okay, so next, about the ROC curve, then we can compute the AOC ROC, right? Using the same command, using the sklearn library. So we got the AOC ROC, and we can also plot the ROC curve for all the 4 models and compare. Right, so we got this ROC curve of the 4 models, and we can see basically all the 4 models performs much better than the no-skill line, which means that our 4 models doing something good. Okay, and from this figure, right, we can see that our MLP seems to be working better than the other 3, because it seems that this MLP has the highest AOC ROC among others models, right? And as you can see, the AOC ROC for our MLP is 0.91, and others are lower than that. So that means in terms of AOC ROC, our MLP model performs the best. Okay. And if we want to do a summary, then we may want to pick just a number of evaluation metrics. And in this case, I want to pick accuracy, F1 score, and AORC, these 3 evaluation metrics, because these 3 are the most commonly used for model evaluation in healthcare. So let's just choose these 3 evaluation metrics, and then we can compare the results for all the 4 different models. So let's so what the cell is basically doing is just creating a table where we can compare all the 4 models in terms of these 3 evaluation metrics. Okay, so let's run it. Okay, so now we got the table, and as you can see, in terms of accuracy, F1 score, and AORC, our MLP or multi-layer perceptron works better than the other 3. So that means that our MLP basically doing the best in terms of these 3 evaluation metrics. But some of you, if you use your own models, probably you may get different results, but it's okay, because you may have different hyperparameter tuning process and then random initialization, which is different from my computer and Hanae computer. So that's fine. But yeah, the purpose of this workshop is just to show you how to implement the models on healthcare data and then how to evaluate it. And yeah, as long as you got it, then totally fine. Okay. So basically, that's the end of the lab, hands-on lab session. And I have just a few messages to say before we ending our workshop. So wait for a while. Okay. So we have finished the hands-on lab session part. And before ending our workshop, I just want to share with you a few messages. So first, let's discuss about some advantages and disadvantages of each machine learning model that we have learned in this workshop. So start from logistic regression. So it is usually the right algorithm to start with in terms of classification tasks. And some of the advantages are, first, it is easier to implement, interpret, and very efficient to train. Okay. And second, the trained model coefficients give inference about the importance of each feature. Okay. And also, it can be easily extended to multi-class classification using a softmax classifier. And this is known as multinomial logistic regression. Okay. And another thing is that the objective functions of logistic regression is convex, as Hanae has explained before. Okay. And however, logistic regression also has some disadvantages. So first, nonlinear problems cannot be solved with logistic regression since it has a linear decision boundary. And in fact, linearly separable data is rarely found in real-world scenarios. Okay. And second, logistic regression requires average or no multicollinearity between independent variables, or otherwise it may temper the model performance. And also, logistic regression also sensitive to outliers. And lastly, if the number of observations is lesser than the number of features, then logistic regression model should not be used, or otherwise it may lead to overfitting. Okay. And now let's discuss about some advantages and disadvantages of support vector machine, or SVM. So some of the advantages are, first, the soft and hard formulation of standard SVM are convex optimization problems and hence have unique global optima. Okay. And second, the hinge loss in SVM often provides higher performance. And SVM also can handle outliers through soft margin constant C. And another thing is a small change to the data does not greatly affect the hyperplane and hence the SVM. So the SVM model is quite stable. And lastly, the kernel trick is the real strength of SVM, as with an appropriate kernel function, we can solve almost any problem or any complex problem. Okay. However, the SVM model also has some disadvantages. So first, when classes in the data points are not well separated, which means that overlapping classes are there, then SVM often does not perform well. Okay. And second, SVM takes a long training time on large data sets, and also choosing an appropriate kernel functions and hyperparameters may be difficult, and it could be tricky and complex. And lastly, when kernel are used, SVM model is often difficult to understand and interpret by human beings. Okay. And now let's discuss about some advantages and disadvantages of K nearest neighbors, or KNN. So some of the advantages are, first, KNN is very easy to implement. There are only one parameter required to implement KNN, which is the value of K. And next, KNN is called lazy learner or instance-based learning. So actually, it does not learn anything in the training period. It does not derive any discriminative function from the training data, or in other words, there is no training period for it. It just stores the training data set and learns from it only at the time of making real-time predictions. And this makes the KNN algorithm much faster than other algorithms that require training, such as SVM. Okay. However, KNN also has some disadvantages. So first, the value of K should be wisely selected since it affects greatly the performance of the model. Okay. And second, in large datasets, the cost of calculating the distance between the new point and each existing point is huge, which degrades the performance of the algorithm. And the KNN algorithm also does not work well with high dimensional data, because with large number of dimensions, it becomes difficult for the algorithm to calculate the distance in each dimension, right? And lastly, KNN is sensitive to noise in the dataset. So we need to make sure to manually impute missing values and remove outliers before applying KNN, okay? And finally, let's discuss about some advantages and disadvantages of neural network. So some of the advantages are, first, neural network has the ability to learn and model non-linear and complex relationships, which is really important because in real life, many of the relationship between inputs and outputs are non-linear as well as complex, okay? And next, neural network learning methods are quite robust to noise in the training data. So the training examples may contain errors, but largely do not affect the final output. And another thing is that neural network can generalize. So after learning from the initial inputs and their relationships, it can infer unseen relationships on unseen data as well, and thus making the model generalize and predict on unseen data. However, neural network also has some disadvantages. So first, which is probably the most crucial one for the application in healthcare, is unexplained functioning of the network. So when neural network gives a probing solution, it often does not give a clue as to why and how. And as mentioned previously, this can reduce trust in the network, right? And second, neural network is also computationally expensive to run and also time consuming. And therefore, it is really hardware dependent. And lastly, there is no specific rule for determining the structure of neural network. So many of the appropriate network structures is often achieved through experience and trial and error, okay? So we have discussed the advantages and disadvantages of the 4 machine learning models that we have trained. So finally, I just want to conclude a few points that we have learned through this today's workshop. So first, we started with a discussion about the overview of healthcare system, such as the types and roles of the healthcare providers, and also the levels of care, right? And we also discussed some of the reasons why we need machine learning to solve some of the problems in healthcare. And second, we learned and implemented some common machine learning models for solving a healthcare problem, including logistic regression, support vector machine, k-nearest neighbors, and neural network. And next, we also learned how to evaluate these models with several common evaluation metrics like accuracy, F1 measure, and AUROC, right? And lastly, we also discussed some of the challenges and issues that arise in implementing machine learning in healthcare, okay? So that is about the end of our workshop. Hanae, if you have any last word to say.
Okay. Thank you for attending the workshop. I hope Ronald and I hope you learned something or that you were interested in the content. Yes, feel free to email us. Also, our supervisors looked okay to share the slides, so we'll come back to you with that. And also the recording of the session should be shared with you when it will be ready.
Okay, so yeah, any last minute questions from the audience, if any? Yeah, okay, so hopefully all of you have learned something useful for your study and career from this workshop. And later on, if you have any questions, feel free to email us. We'll be very happy to have further discussions with you all. Okay, so thank you for joining us for this workshop, and see you. Okay.
Okay, thank you very much. Bye.
Okay, thank you. Bye.